In this deep dive, we'll discuss the paper DeepCritic, Deliberate Critique with Large Language Models.
hmm
It tackles a really interesting challenge as these language models get more powerful. How do we make sure what they produce is actually accurate? And, how can we effectively keep an eye on them? It's becoming a bit like trying to supervise a classroom of increasingly bright students.
Yeah, it really is.
This paper looks at a clever potential solution using other LLMs as critics to automatically review and give feedback on the work of their AI peers.
It's a natural progression, isn't it? I mean, if LLMs can create, the next logical step is, well, can they also evaluate?
Exactly.
However, the researchers behind DeepCritic identified a key stumbling block with the current crop of LLM critics, particularly when you're dealing with complex stuff like, say, mathematics.
And this is where the paper really grabs your attention, I think. They point out that the feedback we're currently getting from these LLM critics in these tricky areas tends to be surprisingly shallow,
Uh-huh.
like surface level. Yeah, it's like they're skimming the surface, but not really diving deep enough to help the original LLM understand why it made a mistake and how to fix it. Think of it like a spell checker flagging a word but not explaining the grammar rule behind it.
Exactly. That's a great analogy. So the DeepCritic paper introduces a brand new approach, a two-stage training process specifically designed to create LLM critics that can provide much more thorough and, well, as the name suggests, deliberate critiques.
So our mission today is to really unpack DeepCritic. We want to understand the specific problem it's trying to solve this issue of superficial feedback and how its novel two-stage process aims to overcome that.
And we'll look at the results too, right?
Oh, yeah, definitely. We'll also be looking at the results the authors achieved, following their line of reasoning every step of the way. Consider this your express lane to understanding some cutting-edge thinking on how we can better oversee these powerful language models.
So good.
Okay, so DeepCritic aims to fix this shallow critique problem. Where do they even begin to address that?
Well, they start by really defining the problem formally. Section 3.1, if you're following along in the paper. They lay out a standard scenario. You've got a math problem, let's call it P, and a step-by-step solution S, which is made up of individual steps chi.
Right.
Now, the job of the critic, which they represent with P, that's the critic model, is to examine this solution step by step and pinpoint the very first incorrect step in the reasoning.
Okay, find the first slip up.
Exactly. Or, if the entire solution is correct, it should just say so. Think of it like a proofreader meticulously going through each line to catch the first error.
Right, so the critic is like a detective trying to find the single point where the logic goes wrong. But, as we were saying, the current LLM detectives aren't exactly Sherlock Holmes in complex situations.
Precisely. The paper really emphasizes that these existing critics tend to offer very surface-level feedback. Instead of truly analyzing the reasoning, they often just kind of repeat the steps of the solution.
Almost paraphrasing it back.
Yeah, something like that.
Mm-hmm.
And this lack of deep critical engagement leads to two major issues. One, they're not very accurate in judging whether a step is right or wrong. And two, even if they do identify an error, their feedback isn't very helpful for the original LLM to learn from and actually correct its mistakes.
And for you, our listener, who wants to grasp the essentials without getting lost in noise, this highlights why effective feedback is key. We want quality over quantity, right?
Absolutely. It's about getting useful signal, not just more output.
Okay, the problem is clear. Current LLM critics are often too superficial to be truly useful, especially in challenging areas like math. So how does DeepCritic actually tackle this? This two-stage pipeline sounds like the heart of their innovation.
It is indeed. Figure 2 in the paper gives a helpful visual breakdown if you want to look it up. The core idea is a two-pronged approach. The first stage is all about teaching LLMs how to critique deeply and deliberately.
Okay, stage 1, teach.
And the second stage then focuses on incentivizing them to actually use those refined critiquing abilities.
Stage 2, incentivize. Got it. All right, let's get into stage 1, teaching LLMs to be deliberate critics. What's the main goal here?
The primary goal of this first stage, detailed in section 3.2.1, is basically to equip LLMs with the capacity to generate really fine-grained and in-depth evaluations of each individual step within a solution.
So not just a thumbs up or down for the whole thing.
Exactly. It's about moving beyond a simple correct or incorrect judgment for the whole solution, or even just for a step. They want detailed reasoning about the reasoning.
And how do they achieve this level of detailed critique? It sounds like there are a few key parts to this stage.
Yes, there are several steps. The first part is what they call initial critique generation. They start by using a very powerful language model, Quen 2.572b instruct. That's a big one on a small set of math problems, and they're correctly labeled solutions from the PRM 800K dataset.
Okay.
Now, here's a crucial point. Instead of having the LLM critique the entire solution as a whole, they specifically instruct it to critique each step independently.
Ah, okay. One step at a time.
Precisely. So for every single line of reasoning, the model has to evaluate its correctness on its own.
That's interesting. So they're really forcing the model to focus on the micro level of reasoning rather than just the overall outcome. The paper mentions equation 2 here. What does that tell us?
Yeah, equation 2 basically formalizes this targeted critique. It just shows that for each step in a solution, they're prompting the Quen 2.5 model to specifically critique that particular step. The output is an initial critique and an initial judgment, like correct and incorrect.
Okay.
This focused approach is a key step in moving away from the superficiality we talked about. However, the authors realized, that this initial critique often involved a lot of direct verification. Essentially, the model just redoing the math itself.
Which is helpful, but maybe not insight.
Right. It might catch calculation errors, but maybe not flawed logic or a suboptimal approach. It could be limiting for getting the deepest level of critical insight.
Okay, so the initial critique is a good first pass, maybe catches the obvious stuff, but it might not be getting at the underlying issues. That brings us to the next part. In-depth critique generation. This sounds like where they really try to elevate the level of analysis.
Exactly. This is really the clever bit, I think. To overcome the limitations of those initial critiques, they prompt the same powerful Quen 2.572b instruct model again.
A second look.
Yeah, but this time, the prompt asks the model to do one of two things. Either evaluate the reasoning from a completely different perspective, or maybe using a different method than it did initially,
Try another angle.
or, and this is really neat, to actually critique the initial critique itself.
Whoa.
Yeah, to see if there were any flaws in its own first-pass reasoning or judgment. Equation 3 describes this second layer of analysis. It's like having a senior reviewer look over the initial reviewer's work, but the same person is doing both reviews with different instructions.
Metacritiquing. So the LLM is not just checking the math, it's also thinking about how well it initially checked the math. That's a fascinating level of self-awareness, computationally speaking.
It is, and this allows for a process of reflection and correction. If the initial critique missed something, or maybe made a faulty assumption, this in-depth critique has a chance to catch it.
Does it actually help? Did they show that?
They did. Table 1 in the paper really highlights the value of this stage. It shows the proportion of initial critiques that were actually corrected or refined through this second round of analysis. It's a significant number, clearly demonstrating the benefit of this reflective process.
Okay, that's convincing.
And importantly, they only keep the solutions for their training data where these in-depth judgments, the corrected ones, actually agree with the ground truth, the actual correct answer or step.
That makes perfect sense. You want to make sure you're building your training data on a solid foundation of accurate critiques. Okay, so after generating these initial and then these in-depth, potentially self-corrected critiques, what's the next step in this teaching phase?
The final step in stage 1 is final critique synthesis. Here, they take the initial critique and the in-depth critique for each step and essentially merge them into a single, coherent, long-form, deliberate critique.
How do they merge them? Just stick them together?
Not quite. They guide this process using in-context learning. They provide the Quen 2.5 model with a few examples. Equation 4 mentions these examples, showing how to combine these different layers of analysis smoothly. Think of it like a writer taking rough notes from different perspectives and then weaving them into a polished narrative.
Ah, okay. So the goal is to make it read as one continuous thought process, like the model thought deeply, checked itself, and came to this conclusion, rather than just presenting two separate critiques just stuck together. The paper mentions specifically trying to avoid phrases like original critique that make sense for creating a natural flow.
Exactly right. And then, as equation 5 shows, these synthesized step-level deliberate critiques are simply concatenated, just joined together to form a complete critique of the entire solution. This includes the final judgment on whether the whole solution is correct or, if not, which step is the first incorrect one. The authors really emphasize that this entire process, the iterative evaluation considering multiple perspectives, the reflection through metacritiquing, is what ultimately leads to much better accuracy in identifying errors compared to simpler methods.
This first stage sounds incredibly detailed and well thought out. It's like they're trying to instill a really rigorous critical thinking process in the LLM before they even start training the final critic model. So, after they have this data set of high quality, deliberate critiques, what do they do with it?
That's where the actual training of the target critic model comes in. They use this curated data set for supervised fine-tuning, or SFT.
Right.
Equation 6 formalizes this. They take this curated data set of deliberate critiques, which they call DSFT. It has around 4,500 examples. And figure 10 in the appendix shows how these critiques are distributed across different types of errors, and they fine-tune their chosen base model on this data.
Which base model did they choose for DeepCritic itself?
For their main experiments, they use Qwen 2.5 7B Instruct as the base model, SFT. So a much smaller model than the one used to generate the critiques.
Ah, interesting. So they use the big 72B model to create the really good examples and then teach a smaller 7B model using those examples.
Exactly. Think of this SFT step like showing the 7B model a lot of really good examples of how to perform deliberate critique so it learns the pattern and style they're looking for. The key here is that this SFT process teaches the model the format and structure of these detailed deliberate critiques.
Okay, so stage one is all about creating this really valuable training data of deliberate critiques using a powerful teacher model, and then using supervised learning to teach a smaller student model how to produce them. That leads us naturally to stage two, incentivizing LLMs to deliberately critique. What's the reasoning behind this second stage? Why isn't SFT enough?
Well, the idea behind stage 2, which is outlined in section 3.2.2, is that even after learning the how of deliberate critiquing through SFT, the model might still have room to improve in terms of the quality and accuracy of its critiques. SFT teaches the format, but maybe not perfect judgment in all cases.
Okay, fine-tuning the judgment itself.
Right. So this stage uses reinforcement learning, or RL, to further enhance its critique ability by rewarding it specifically for giving better, more accurate judgments.
And I see they explore two different RL setups based on where they get their data. Let's start with the first one, where they use human-labeled data. That sounds straightforward.
Yeah, that's setting one. In situations where high-quality human-labeled data is available, they can directly use it. For this paper, they leveraged the existing PRM 800K dataset, which contains a substantial 40,700 data points suitable for this purpose. Figure 11 shows the label distribution for that.
Wow, that's a lot of data.
It is. And the logic here is pretty clear. These human annotations provide a very strong, reliable signal for what constitutes a correct and helpful critique step. So you reward the model for agreeing with the human judgment.
That makes sense. Use the gold standard when you have it. But what about situations where we don't have access to such a large amount of human-labeled data? That can be expensive and time-consuming to create. That's where the second RL setting comes in, right?
Exactly. That's setting 2, designed for scenarios where getting human annotations is impractical or too costly. Here, they developed a method for automatic data generation for the RL training.
Automatic data generation for RL. How does that work?
It involves using a technique based on Monte Carlo sampling to estimate how likely each step in a generated solution is to be correct. Think of it like running simulations to see how often an error at a certain point propagates and leads to a wrong final answer downstream.
Okay, sounds a bit complex. Can you break down how this automatic data generation process works?
Sure. They start by taking math problems from a few different data sets, GSM-8K, math, and some Olympiad problems from Newman Math Coty. Then, they use smaller Qwen 2.5 language models like the 1.5B, 3B, 7B parameter versions to generate multiple different step-by-step solutions for each problem.
Why multiple solutions?
To get variety and, crucially, to find solutions with errors. They then filter out the problems where all the generated solutions are either entirely correct or entirely incorrect.
Why filter those out?
Because those cases don't give much information for learning how to critique errors or differentiate correct from incorrect steps. They're really focusing on the messy cases where mistakes happen somewhere in the middle.
Okay, so they're focusing on the solutions that have some errors in them. What happens next? How do they automatically pinpoint the first mistake without a human looking at it?
Right, this is the clever part for the incorrect solutions. For each step in the solution, they imagine stopping the solution at that point. Then they have another LLM, in this case, Qwen 2.57B Instruct, try to complete the reasoning from that point onwards multiple times. They do this rolling out process n times, and in their experiments, n was 8.
Okay, 8 attempts to finish the problem from that step.
Exactly.
Yeah.
Now, if, from a particular step onwards, all 8 of these rollout attempts consistently lead to incorrect final answers, While for the previous step, more than half say 5 out of 8 or more of the rollouts led to correct answers, then they identify that specific step as the likely first erroneous one.
Ah, I see. It's where the probability of reaching the right answer suddenly drops off a cliff.
Precisely. It's a probabilistic way to pinpoint the likely origin of the error. They use a similar process, by the way, for solutions that have a correct final answer but might have incorrect intermediate steps, trying to find those hidden flaws too. This whole process allows them to automatically construct a dataset for RL with around 14,200 examples. Figure 12 in the appendix shows the label distribution for this automatically generated dataset.
That's a pretty ingenious way to get labeled data for reinforcement learning without needing humans to go through every single tedious step. It really highlights how important getting good training data is, whether human or automatically generated, for improving these critique models.
It absolutely is. The quality of the data used for RL is crucial. Both RL settings, whether using human labels or this automatic method, aim to further refine the critique abilities that the model learned during the SFT stage, pushing it to become even more accurate and insightful in its evaluations.
All right, so we've taken a pretty deep dive into the two-stage deep critic methodology, the teaching stage with SFT and the incentivizing stage with RL. Now let's move on to section 4 of the paper and discuss the experiments they conducted to see how well it actually works in practice. What were the key experimental setups?
Okay, yeah. Section 4.1 details their experimental setup. As we mentioned, they used Quen 2.57b instruct as their base model.
The 7 billion parameter one?
Right. And then they created 3 different versions of DeepCritic based on the training. One that only went through the supervised fine-tuning stage using their generated critique data. That's DeepCritic 7b SFT.
Okay.
Then one that was further trained with reinforcement learning using their automatically generated data. DeepCritic 7b RL Nimina.
The Monte Carlo method data.
Exactly. And finally, one that used the human-labeled PRM 800K data for RL. DeepCritic 7b RL PRM 800K.
Got it. So SFT only, RL with auto data, and RL with human data.
Yep. So we have a basic fine-tuned version, a version trained on AI feedback, and a version trained on human feedback.
And how did they put these models to the test? What benchmarks did they use to see if DeepCritic was actually better at finding errors than other approaches?
They evaluated these models on 3 pretty well-regarded benchmarks, specifically designed for error identification in math reasoning. First is MRGSM8K, which is a subset of the standard GSM8K math word problems, but focused on ones requiring meta-reasoning.
Okay.
Second is PRM800K, specifically the Phase 2 test set, which comes from the same source as some of their training data, but is held out for testing.
Makes sense.
And third is Process Bench. This is a more comprehensive benchmark made up of 4 different subsets, pulling questions from various sources like GSM8K again, the math dataset, Olympiad Bench, and OmniMath. So a good mix of problem types.
And what do these benchmarks actually provide?
All of them basically give you a problem, a proposed step-by-step solution, and crucially, a label that tells you which step is the first incorrect one, or if the whole solution is actually correct. Appendix B.2 has more details if you want the nitty-gritty on the benchmarks.
Okay. And to see how DeepCritic stacked up, they tested it against a range of other models, right? Who were the main competitors in this showdown?
Yes. They compared DeepCritic against 2 main groups of models to provide context. First, they looked at other process reward models, or PRMs. These are models specifically trained to evaluate the correctness of reasoning steps. Kind of like DeepCritic, but maybe trained differently.
Like other attempts at this kind of critic.
Exactly. They included models like Math Shepherd PRM7B, RLH Flow PRM8B, which uses either Mistral or DeepSeek as the base model, and also Quen 2.5 Math 7B PRM800K, which is based on the same family as DeepCritic's base model, but trained differently as a PRM.
Okay, so specialized reward models. What was the second group?
The second group was standard LLM critics. Here, they just took several leading large language models off the shelf and prompted them to act as critics without specific fine-tuning for this task in the same way as DeepCritic.
So just asking a smart model to critique.
Pretty much. This included models like LMA 3.1, both the 8 billion and 70 billion parameter versions.
Okay.
Various versions of Quen 2.5, again, different sizes, and some that were already fine-tuned for general math problem solving. The big one, GPT-4o.
Ah, the benchmark everyone compares against.
Right. And even some very strong reasoning LLMs like DeepSeek R1 Distill, using both Llama and Quinn variants as their base models. So it's a really comprehensive set of comparisons covering both specialized models and general purpose powerhouses.
That's a pretty thorough gauntlet to run. What about the specifics of how they trained and evaluated their DeepCritic models and these other systems? Any important details there?
Yeah, they provide quite a bit of detail. For the supervised fine-tuning of DeepCritic, they use specific settings for hyperparameters like the learning rate, batch size, and the number of epochs, how many times they went through the training data.
Standard stuff for training.
Right. And similarly, for the reinforcement learning stage, they used a particular framework called VERL and an RL algorithm called GRPO. They also had to define the reward structure, how the model gets rewarded for correct judgments, and set specific learning rates, epochs, and other technical parameters, like the KL coefficient, to keep the model from changing too drastically from the SFT version. Figures 8 and 9, plus Appendix B.3, have all those fine-grained details, if you're into that.
And the evaluation, how did they ensure a fair comparison?
For the evaluation, they aim for consistency. They use the same settings across all models when generating the critiques, things like the sampling temperature set to 0 to be deterministic, top, and the maximum length of the generated critiques. For the main results in the table, they only sampled one critique per model per problem.
Okay, one shot per problem.
Yeah, exactly. Their evaluation prompt, which asks the model to identify the first incorrect step or confirm correctness, was based on previous research, but they modified it slightly to encourage more reasoning in the output. That prompt is in Appendix B.4. And the main way they measured performance, the primary metric, was the F1 score.
Why F1?
F1 score is the harmonic mean of precision and recall, or in this context, accuracy on incorrect solutions and accuracy on correct solutions. It's a good overall measure, especially useful when you might have an imbalance like maybe most solutions are correct and only a few have errors. It balances finding the errors with not falsely accusing correct solutions.
Right, balances false positives and false negatives. Okay, so with all those pieces in place, the models, the benchmarks, the training, the evaluation, what were the main findings? What did Table 2 in the paper actually tell us about how well DeepCritic performed against all those other models?
Okay, yeah, Table 2 is where the headline results are. The first thing they observed, which kind of confirms their motivation, is that existing smaller language models, when just instructed to form critique without special training like DeepCritics, generally don't do a very good job. They show pretty low F1 scores, low accuracy.
So the initial problem statement holds up.
It does. And unsurprisingly, larger, more capable language models tended to perform better just off the shelf. That makes sense.
Okay, what else?
Secondly, they noticed that models specifically known for their strong reasoning abilities, like those DeepSeek R1 Distill models, also showed better critique performance than standard instruction-tuned models of similar size. This suggests that, the ability to reason well itself can transfer somewhat to the task of evaluating reasoning. Good reasoners make better critics, basically.
It seems intuitive. But the most important results are about DeepCritic itself, right? What did they discover there? How did their models do?
Absolutely. This is the core result. The first crucial finding is about their DeepCritic 7B SFT model, the one that only got the supervised fine-tuning on their deliberate critique data.
Right, the first stage only.
This model showed a really significant improvement over the base Quen 2.57b instruct model it started from. They mentioned about a 20-point jump in the average F1 score across the benchmarks. That's huge.
Wow, just from SFT on that special data.
Yeah. And what's perhaps even more impressive is that its overall performance was comparable to the much, much larger Quen 2.572b instruct model.
So the 7B SFT model performed like the base 72B model.
Roughly, yeah. On average across the benchmarks. This strongly suggests that the quality of their curated deliberate critique data and the specific training in that format are really effective. It allows a smaller model to punch way above its weight, performing at a level close to a model 10 times its size. That's a potential game changer in terms of efficiency and cost.
That's a massive leap in performance just from that first stage of supervised fine-tuning. That really validates their data generation process.
What about the impact of the reinforcement learning in the second stage? Did that provide an additional boost on top of the SFT?
Yes, it did. The RL stage provided a further noticeable increase in performance. Their DeepCritic 7B RL Numina model, remember, that's the one trained using their automatically generated data.
The Monte Carlo simulation data.
Right. That model showed another significant improvement over just the SFT model. On the main process benchmark, for example, the average F1 score jumped from around 54 for the SFT model to about 63.5 for the RL Numina model.
So RL definitely helped further.
It did. And this is really promising because it suggests that we might be able to use these automated methods like their Monte Carlo estimation to effectively generate data to further enhance the critique abilities of LLMs, potentially reducing the reliance on expensive human labeling for this RL step.
Okay, and what about the final version, the one trained with human-labeled RL data, the DeepCritic's 7B RL PRM 800K? How did that one do? That was the top performer. This model, which benefited from both the SFT stage and the RL stage, using the high-quality human-labeled PRM 800K data, actually outperformed all of the other models they tested on most of the benchmarks.
All of them, including GPT-4o and the specialized DeepSeek models.
Yes, including GPT-4o and the similarly sized DeepSeek reasoning models. It achieved the best overall average F1 score across the board. This was their headline result, really demonstrating the power and effectiveness of their complete two-stage training approach.
That's seriously impressive for a 7B parameter model.
It really is. The overall conclusion the authors draw from this section is clear. Their proposed two-stage training pipeline is highly effective in enhancing LLM critique and verification abilities, especially for complex reasoning tasks like mathematics.
These results look really compelling, showing that DeepCritic can indeed lead to much more capable LLM critics, outperforming even much larger models or models specifically designed for reasoning. Now, the paper also explores something called test time scaling results in Section 5. What were they investigating there? What does that mean?
Yeah, Section 5 explores an interesting question. The authors were curious to see what happens if you invest more computational effort at the time of testing, not during training, but when you actually use the model. They wanted to see how the DeepCritic framework performs under these conditions, looking at scaling compute for both the critics themselves and for the language model generators whose solutions are being evaluated.
Okay, so spending more time or resources during inference.
Exactly. For these experiments, they focused on their best performing model, DeepCritic-7B RL PRM 800K, which they often just refer to as DeepCritic 7B RL for simplicity in this section, and they compared its scaling behavior against the base Quen 2.57B instruct and the strong reasoning baseline DeepSeek R1 Distill Quen 7B.
Let's start with the test time scaling of the critics themselves. How can you scale the critics' compute at test time?
In section 5.1, they looked at a common technique, majority voting. The idea is simple. Instead of running the critic just once on a given solution step, you run it multiple times, say 8 times, using slightly different random seeds or sampling parameters if applicable, though here they likely just ran it deterministically multiple times. Then you take the judgment, correct step X, that appears most frequently among those 8 runs as your final answer.
Like asking for a second, third, fourth, eighth opinion from the same expert.
Pretty much, yeah. They specifically looked at running each critic 8 times and taking the majority result, a technique often called MOJ at 8 or similar.
And what did they find when they applied this majority voting technique to DeepCritic and the baselines? Did it help?
Yes, it did. As shown in one of the figures, figure X, let's call it, we'll link the exact one, they found that using majority voting generally improved the performance, the F1 score, for all the critic models they tested. More compute led to better results. It was good to see.
Okay, that's expected maybe. How did DeepCritic compare?
Importantly, the MAGE at 8 performance of their DeepCritic 7B RL model was better than that of the strong baseline DeepSeek R1 Distill Quen 7B in several cases, and its average F1 score using MAGE 8 was also higher overall. This indicates that DeepCritic not only performs well with a single pass, but also benefits nicely from this increased test time computation. It scales well.
That's good to know that simply asking the DeepCritic model to evaluate a solution multiple times and taking the consensus can lead to even more accurate error detection. Now, what about the other side of the coin? Using these improved critics to actually help the LLM generators themselves get better. Section 5.2 looks at this, right? They mentioned 2 main ways they explored this.
Yes, exactly. Section 5.2 investigates how DeepCritic could be used to boost the performance of the LLMs that actually generate the math solutions in the first place. The first method they looked at is called verified majority voting.
Verified majority voting. How is that different from the critic majority voting?
It's similar in spirit, but applied differently. Here, you have the generator LLM produce multiple potential solutions to the same math problem, say 8 or 16 different attempts.
Okay.
Then you use your critic model, like DeepCritic, to evaluate each of those generated solutions. You filter out or discard The solutions that the critic identifies as incorrect.
Ah, use the critic as a filter.
Exactly.
Hmm.
And then you perform majority voting only on the remaining solutions, the ones the critic thinks are correct. The hope is that this filters out the bad attempts and leads to a better final answer from the consensus of the good attempts. They also had a fallback mechanism, like if the critic flagged all the generated solutions as incorrect, they'd just do regular majority voting on all of them.
Which generators and critics did they test here?
They used Quinn 2.57b instruct and the much larger Quinn 2.572b instruct as the generators. The critics were DeepCritic 7BRL and the baselines. And they evaluated the final answer accuracy on math and name benchmark problems using MathVerify, which is a separate, reliable rule-based system, just to check the final numerical answer.
Okay, and what were the outcomes of this verified majority voting approach using DeepCritic?
The results are shown in another figure, let's call it figure Y. They found something important. If you use a weak or unreliable critic as the verifier in this process, it can actually hurt the generator's performance.
How so?
Because a bad critic might incorrectly discard correct solutions, leaving you with only incorrect ones, or just reducing the pool of good candidates for the final majority vote. Garbage in, garbage out applies to the critic, too.
Makes sense. The filter needs to be accurate.
Precisely. However, the good news was that their DeepCritic 7BRL model, being a much stronger critic, led to greater improvements in the generator's majority voting performance compared to using the baseline critics, especially in most of the sampling settings, like when generating 8 or 16 solutions. This really underscores the value of having a good, accurate critic like DeepCritic in this kind of verification loop.
It really does highlight that the quality of the critic is paramount if you want to use it effectively to improve a generator. What was the second way they explored to improve generators using these critiques? You mentioned critique-based refinement.
Right. The second approach discussed in section 5.2.2 is critique-based refinement. This is perhaps more intuitive. Here, the generator produces an initial solution first.
Okay, just one solution.
Yeah. Then, the critic model, DeepCritic, or a baseline, provides feedback on that specific solution, pointing out the likely first error.
Like we saw in the main results.
Exactly. And then, the original generator LLM tries again, attempting to revise its solution based on the critique it just received. They use greedy decoding, just taking the most likely next word, for the generators in these refinement experiments to keep things deterministic and comparable.
So generate, get feedback, regenerate, a sort of iterative improvement loop.
Precisely. And Table 3 in the paper shows the results for this. They look at some interesting metrics. WESC, which is the percentage of initially wrong solutions that became correct after refinement.
Okay, how often it fixes mistakes.
CAW, the percentage of initially correct solutions that unfortunately became wrong after refinement.
Oops, how often the feedback makes things worse.
Right. And of course, the overall final accuracy after one round of refinement.
And what did they find when they had the generators refine their answers based on DeepCritic's feedback compared to the baselines?
Well, first they noted a potential issue with one of the baseline critics, DeepSeek R1 Distill Quinn 7b. They suspected it might have inadvertently been exposed to the correct answer or reasoning patterns during its own training or critique generation process, potentially leaking the answer in its critique, which would unfairly inflate its refinement performance. So they presented its results separately as potentially optimistic.
Okay, good. They noted that caveat. What about DeepCritic versus the other baselines?
The key finding here was that their DeepCritic 7b RL model was significantly more effective at helping the generators correct their errors. It had a higher WC rate compared to the base Q model used as a critic. This was true even when helping the much larger Quinn 2.570b generator.
So the smaller 7B DeepCritic could help the bigger 72B model fix its mistakes.
Yes, exactly. Because DeepCritic provides more detailed, accurate, and insightful feedback about where the error likely is, the generator model, even the big one, can use that feedback more effectively to revise its reasoning and arrive at the correct solution. This demonstrates the really exciting potential for what's called weak to strong supervision.
Weak to strong.
Yeah, where a smaller but more capable or specialized critique model, the weaker one in terms of size perhaps, but stronger at critique, can guide and improve the performance of a larger, more general, but potentially flawed generation model, the stronger one in terms of size or raw generation power.
That's a really significant and potentially very valuable insight, that a carefully trained critique model like DeepCritic can help even more powerful models improve their reasoning.
Okay, so to bring it all together now, what are the main conclusions that the authors draw in section 6 of the paper, wrapping up their work?
In their concluding remarks, the authors summarize their key contributions pretty nicely. They highlight the novel two-stage DeepCritic pipeline, that SFT followed by RL process. They emphasize the careful and detailed method they developed for constructing their long-form deliberate critique dataset, which was crucial for the SFT stage.
Right.
And of course, they point to the strong performance that their deep critic models achieved on the various error identification benchmarks, consistently outperforming strong baselines.
And the implications.
They emphasize the significant potential of deep critic, not only for just supervising LLMs passively, but also for actively improving the reasoning capabilities of large language models, even as we just discussed, those models that are more advanced or larger than the critic itself. That weak to strong potential.
They end by expressing their hope that this work provides valuable insights for future research in these areas, particularly in deliberate reasoning, getting models to think more carefully, and also in developing scalable oversight mechanisms for increasingly powerful AI systems.
So for you, our listener, wrapping up this deep dive into the DeepCritic paper, the key takeaway is that it represents a really significant step forward in our ability to automatically evaluate and, crucially, improve the outputs of large language models, particularly in those really complex reasoning tasks like mathematics. It directly addresses that initial problem we discussed, the often superficial nature of feedback from current LLM critics, by introducing this rigorous two-stage training process, first teaching the format and then reinforcing the accuracy.
Absolutely. For me, the real aha moments are, first, just how effective that two-stage approach proved to be, especially the cleverness of the in-depth critique generation in stage one, the metacritique idea.
Yeah, the self-correction part.
And then showing how reinforcement learning, whether with human or automatically generated data, could further sharpen those critiquing abilities. And second, as we just discussed, that surprising and potentially transformative finding that a smaller, well-trained 7B critic can actually guide and improve the performance of a much larger 72B language model. That really opens up some incredibly exciting avenues for the future of AI development and oversight.
It really does. It makes you think, doesn't it? Considering the rapid advancements in this field, what other innovative ways could we leverage LLMs to supervise and enhance each other in the years to come? Could we have chains of critics, or critics specializing in different types of errors?
Or critics that learn alongside the generator. Lots of possibilities.
Yeah, and what are the broader implications for how we build more reliable and trustworthy AI systems, especially as they tackle more complex problems? Definitely some food for thought there.
For sure.
If you'd like to delve even deeper into the specifics of this research, all the equations, figures, and detailed results we mentioned, we highly recommend checking out the DeepCritic paper itself. You can find it on OnCiv or the usual places.
Agreed.
It really is a fascinating look into the cutting edge of LLM research and this critical area of oversight and improvement. Thanks for joining us for this deep dive.